Okay, this will be chapter 25. We'll be taking a look at electromagnetic induction, and I'll talk a little bit about what that is, and I will warn you ahead of time that it's a slightly more complicated than usual concept, not because it's extremely difficult, just because it's hard to conceptualize. So I'll talk about what induction is, I'll talk about Faraday's law, which kind of describes it. I'll talk about how we can generate power and why we use AC inside of our houses. We'll talk about power production and power transmission, and I'll finish off by leading into the next chapter, which is about light. So, what exactly is electromagnetic induction? Well, someone very wise once said that nature abhors a change, and technically they were talking about the change in magnetic flux. Now, I always like to think about it when I think about my mother. And one time when I was growing up, she had this horrible yellow carpet, and we go into the carpet store to buy a new one, and she wants the same exact color, and it was like straight from the 70s. And what she said to the salesperson just floored me. She said, "Well, I don't like change," and she was very adamant, and eventually settled for a nice brown. Now, when I'm talking about electromagnetic induction, it turns out that if you have a coil of wires and you take a magnet and you hold it near it, then absolutely nothing is going to happen. However, once we start to have this important thing, this thing called change, then nature's going to oppose that change. So as soon as this magnet starts to move into the coil of wires, it's actually going to induce a voltage and a current. And what that voltage and current is going to do is that's going to take my little green ring and it's going to try to stop that change. So if I try to lead in with a north edge, then the current's going to set up around this such that it looks kind of like a magnet. So what we're doing is we're inducing a voltage by changing the magnetic field. Change is an important word for this particular chapter. So change. No change, no voltage. So kind of what we're doing is we're forcing a change in the magnetic field. So we're going ahead and we're taking our magnet and we're going to put it in there like that, and that's going to set up an electric field. Electric field is going to set up current, and we know that a current flowing through a wire is going to generate a magnetic field. And again, the direction is going to oppose the original change. So this thing might get some current in this direction, and then this ring is going to start to look like a magnet, at least to this guy, and then the magnetic field is going to try to stop the change of that original magnet going down into it. Now, this is kind of interesting, but that production of voltage is actually kind of useful because we can use that for minor things like generators. So very often we want to increase that induced voltage, and what we can do is we could say, okay, well, more coils of wire meant more magnetic field before, so more coils of wire are going to mean higher voltage. It turns out that the speed of the magnet is going to make a difference. Slow motion is not going to hardly produce any voltage, and rapid motion is going to produce a much greater voltage. And I'll show you what I mean by that. So here I have the same simulation that I showed you earlier, but here I have a coil of wires, and here I have a magnet, and you can kind of see that if there's no change, then there's no voltage induced. I start to change the magnetic field inside of this guy, and I start to get some voltage. My light bulb starts to light up. Going slow, not producing a whole lot of voltage. Going fast means lots and lots of voltage. We can also increase the number of coils. Increasing number of coils should produce more voltage. So this is essentially more or less how generators work. Here I have a light bulb, here I have a magnetic field, and it turns out it doesn't matter whether I make it go through or if I just change the magnetic field inside of it. And you can kind of see that as this thing spins around, first it's going to have north and then south and then north and south, and that's going to induce a current that's going to oppose that change inside of this coil of wires. And that's more or less what electromagnetic induction boils down to. Just a quick little check your neighbor. I haven't done one of these for a while, but more voltage is induced when a magnet is put into a coil more quickly. More change, the faster it is, the more voltage that we're going to induce. Something else that's kind of interesting is it actually doesn't matter whether the magnet moves or whether the wire moves. The fact that there is change, just the very nature that there is change, is actually going to induce the induction. So the magnet could go up and down, or the wire could go up and down through the magnet. Pretty much they're all going to induce some voltage, as you can kind of see on the readings right here and right here. Now, this slide right here just kind of shows you everything that I showed you with that simulation when I messed around with the number of coils, and you can kind of see that if I only had 2 coils, I might get a voltage of 2. If I had 4 coils, I might get a voltage of 4 volts, 6 coils, and 6 volts. So pretty much the voltage is going to be directly proportional to the number of coils. That's more or less what Faraday's law essentially says. Faraday's law says that the voltage that induced is going to be directly proportional to the number of coils, and the rate of change, how quickly the magnetic field changes. We can also put this in the language of current if we were to talk about resistance, but Faraday's law largely deals with the voltage that is induced. Faraday's law also says that if we were to try to take a magnet and shove that magnet into a coil of wires, that nature is going to oppose that change, and actually it's going to be hard because each loop that we have is going to act like a little teeny tiny magnet. And again, if I were to just take my north and my south and drop it in, then this thing's going to go ahead and look like a north and a south. If I were to do the same exact experiment, but rather than use a south and a north, then nature is going to induce a current in the opposite direction, and that would make it look like a south and then a north right here. And I actually have a nice little demonstration of this for you all. So here's an example of Faraday's law in action. Here I have a copper pipe and a magnet and a ball bearing in my hand, and neither of them are attracted to the copper pipe, which is expected because the copper is not ferromagnetic. When I drop the magnet through it, it takes a long time. What's going on is it's inducing little magnets that slow this thing down. It's opposing the change. I drop the ball bearing, as I am right now, it goes right through it. It does not have a magnetic field to oppose the change. Again, if I drop the magnet through it, you can see it takes quite a long time. This is Faraday's law in action. Another example is here I have a coil of wires with a magnetic or with an iron core, and if I put a ring on top and turn it on, run alternating current through it, the ring jumps up. It's acting like the opposite pole of a magnet. Lastly, I have the same device, and it's a coil of wires, and I'm going to put a coil of wires with a light bulb on there, and it doesn't need to physically touch the circuit. I drop it in there. It can even be in water. I can stick my hand in there. The light bulb is going to light up, and I'm perfectly fine. Now, this just kind of says in text everything that I've already said, but Faraday's law essentially says we can induce voltage, and to induce the voltage, we have to have change. Change. And if we had a loop and we had a magnet near it, that if there was no change, then absolutely nothing's going to happen. Once we start to change the magnetic field inside of that loop, then we're going to start to get some voltage. And as I said, it doesn't matter whether the loop moves or whether the magnet moves. Either one is going to induce a voltage. Something else we could do is we know that if we had a loop of wires over here with some current flowing in it, that's going to look and taste and feel just like a magnet. So we could also have a nearby loop, and if we mess around with the current in this loop, that's going to mess around with the magnetic field that it sends into this loop, and that would also cause a change in that loop. So all three of those are more or less equivalent. Kind of some applications of this. If you've ever driven through an old town and you were to look at the white line where you're supposed to stop at when you get a red light, then maybe you've seen something that looks like a square right here. Now, what that square essentially does is that square is looking for a change, and when your car goes over it, then it's putting a piece of iron into this current-carrying loop, and it can actually sense that change. Nowadays, most of them use, most of those guys, you just use traffic cameras. This is more or less how that security system in the airport works. If you have some metal in your pocket, you walk through it. It's got a magnetic field. You put some metal into that magnetic field, and bada boom, you have some change. You're going to have some induced current, and it can sense it. Credit cards, at least the older ones, now these chips make a difference. They only work when the credit card was swiped. There needed to be some change. What was changing? Well, on the very back of that credit card, there's a magnetic stripe, and it had to change and go through the sensor in order for that to work. Even older, things like tape or old school hard drives, there needed to be some change. There had to be some physical movement of some piece of metal in a magnetic field, or near a magnetic field. Now, kind of some implications of this is actually going to be a generator, and this looks just like the motor I showed you in the last chapter, but the difference is now we're converting mechanical input into electrical output instead of electrical input into mechanical output. But pretty much it works the same way. What we're doing is we have this wire that's inside of this magnet. The magnet has a north, the magnet has a south. And what we do is we put some mechanical energy into it, and we're going to have a piece of metal moving in a magnetic field. It's going to produce an electrical field. It's going to produce a voltage, and we could turn that voltage into something that would go through a light bulb or something like that. Something that's kind of interesting is the voltage is actually alternating, because direction does kind of matter, and it matters whether this thing is kind of going right or going left. Let's just for a quick second look at the voltage that is in this coil right here, and that voltage is going to be positive when this thing is spinning like this. It's actually going to be 0 when it's perpendicular to it. It's going to keep on rotating, and it's actually, the voltage is going to go positive, negative, positive, negative. So technically this needs to have some alternating current, or this is going to generate alternating current. It's not going to generate direct current. And we actually kind of saw that when we took a look at my simulation from earlier. What we can kind of see in this particular simulation is I've got my mechanical input, that's this guy over here, and you can see first the electrons go clockwise, and they go counterclockwise, and then clockwise, counterclockwise, clockwise, counterclockwise. This is called alternating current, and we talked about that earlier. It's kind of when the current sloshes back and forth. It doesn't go in just a direct loop. So here's an example of Faraday's law in action. Here I have a copper pipe and a magnet and a ball bearing in my hand, and neither of them are attracted to the copper pipe, which is expected because the copper is not ferromagnetic. When I drop the magnet through it, it takes a long time. What's going on is it's inducing little magnets that slow this thing down. It's opposing the change. I drop the ball bearing, as I am right now, it goes right through it. It does not have a magnetic field to oppose the change. Again, if I drop the magnet through it, you can see it takes quite a long time. This is Faraday's law in action. Another example is here I have a coil of wires with a magnetic or with an iron core, and if I put a ring on top and turn it on, run alternating current through it, the ring jumps up. It's acting like the opposite pole of a magnet. Lastly, I have the same device, and it's a coil of wires, and I'm going to put a coil of wires with a light bulb on there, and it doesn't need to physically touch the circuit. I drop it in there. It can even be in water. I can stick my hand in there. The light bulb is going to light up, and I'm perfectly fine.